We are now to a point where we want to begin to use the Laplace transform to do the things that it's really powerful in doing. And that is to talk about transfer functions. And of course, in this semester, we'll talk about transfer functions in circuits. And also to begin an introduction to filtering. And we'll not get to that in this particular lecture, but it will be the lecture that immediately follows. So what we're really doing here is we're going to find the transfer function from common circuits that involve R, L, and C. So as a way of introduction, let's talk a little bit about a transfer function. In general terms, the transfer function is determined for a system by finding the ratio between the output of a system divided by the system input in the Laplace domain. So in the time domain, the transfer function would be the impulse response. In other words, sort of the defined response of a circuit to an impulse input. It's a lot easier to work with transfer functions than it is impulse responses for several reasons. First, they don't involve differential equations or time domain functions, and specifically they don't involve convolution integrals. Rather, they just involve basic algebra. So in a circuits application, the transfer function is an output over an input. Technically, it doesn't have to be unitless, but in practice, we almost always put the system parameters in terms of an output voltage over an input voltage. The transfer functions have two main applications. They have two main applications. First, to find a way to characterize a system that is independent of any input forcing functions. And secondly, to determine the frequency response of a system. So let's talk just a little bit about the first one, because we won't put a lot of emphasis on the first one, so we'll do most of our discussion on that today. So basically, if you have a system and you know where you'll have an input and where you'll take an output, what the transfer function does is it gives you a way to do everything except the analysis of a source. So I should at this point mention that when we find the transfer function of a circuit, we do not have sources in that circuit. It's just going to be a network of resistors, capacitors, and inductors. You can also find a transfer function of a circuit that contains an op-amp, and we'll do that later as well. So basically, and you've actually in circuits, you probably already did something like a transfer function when you calculated the output of an inverting amplifier, because it was basically, you could get a ratio of output over input. So if you have this way of characterizing a network just from its passive elements, then basically you get this function, and all you have to do then is multiply it by the input voltage. And so the input voltage could be changed. You could find the response of the circuit to a sinusoidal voltage, to a pulse, to a series of pulses. So anyway, that becomes very convenient. So let's first of all look at what we mean by a transfer function and determining one. So we'll start with this simple example. We have this RC circuit. And so I should point out first of all that the transfer function of a circuit depends on where the input and where the output are taken. So in this example, you can see the input voltage between these two terminals is going to drop across both R and C. The output voltage, though, is taken only over R. So as you calculate different transfer functions for this particular circuit, you could see there would be two possibilities. One would be to take the output voltage over the resistor. The other would be to take the output voltage across the capacitor. The transfer function will change, but as you'll see, the poles, the denominator of the transfer function will not change, and the poles will remain the same. So first of all, in order to find a transfer function, you have to transform your circuit to the Laplace domain, which means this capacitor would become 1 over SC. The resistor remains a resistor. The voltages become voltages in the Laplace domain, functions of S. So then what you do is you basically find a way to calculate the output voltage in terms of the input voltage. For this problem, that's very simple. It's a simple voltage divider. So I just take the voltage across the impedance that I want, which is R, and then I divide that by the sum, R plus 1 over SC, multiplied by the input voltage, and that's going to be my output, the simple voltage divider rule. And then remember, the transfer function is output divided by input. So if I take this equation and I divide both sides by V sub input, then I get the transfer function H of S. So once again, this quantity, H of S, gives you the ratio in the Laplace domain of the output voltage to the input voltage without specifying what the input voltage is. So it's independent of any sources and dependent only upon the network topology of the passive elements. Okay, now let's look at what happens if we take the output over the capacitor. So this is the exact same thing. You would once again transform the circuit, and I can't emphasize how important this is. I actually have some people who take this class and try to find a transfer function in the time domain that just doesn't exist. So we transform the capacitor, we do the same kind of voltage divider, this time taking our output across the 1 over SC impedance, and when I solve for that, I get the following transfer function. You can see it is a little bit different. We'll look at the one we had before. Notice the one we had before has an S in the numerator. Notice this one has 1 over RC in the numerator. But notice this denominator, S plus 1 over RC, is common to both. Remember, it is the denominator of a transfer function when you do the partial fraction expansion. So rather than talking about transfer functions, let's just talk about any function in the Laplace domain. When you do the partial fraction expansion, it is the denominator that's going to give you the functional form in the time domain. When you take the inverse transform, the function in the time domain, what kind of function it is, comes from the denominator. So what this says is that we've got this denominator, S plus 1 over RC. The inverse transform of terms like that, as a general rule, is going to look like e to the minus 1 over RC times t. So that kind of term is going to show up to be common in all of these. So just saying, that's going to be a common thing, and we'll see that as we proceed with some of the problems. All right, once again, this gets a little redundant, so I'm not going to go in great detail. You can do the same thing with an RL circuit. You can take an RL circuit, you take your output across the resistor, and you get this transfer function here. And notice that this transfer function has a similar form to the transfer function when we had the RC circuit and took the output across the capacitor. Here we have replaced the L with an SL. Likewise, you can do the same thing, take the output across the inductor instead, and you get a transfer function with an S in the numerator, but the denominator, once again, is the same. R over L is in our denominator, so our pole for this transfer function would be at minus R over L. Remember that the pole is it's the values that make the denominator go to 0. It's the roots of the denominator. And we'll show one more. This is a common RLC circuit. I know we skipped these in circuits 1. I just wanted you to see that you can find a transfer function for an RLC circuit. I did it exactly the same way. I used a voltage divider, finding the output voltage across the resistor. You could also take it across the inductor and the capacitor. You can even do a transfer function over 2. So I could have, if I wanted to, taken a transfer function across this series combination, and in fact there is a type of filter that does that. But for now, for this example, we've taken the output across the resistor. So taking the output across the resistor, remember, a voltage divider can work for any number of things in a string. And so if we take the output across the resistor, we get this expression. And then we solve it for V out over Vn, giving us a transfer function. And also notice between this step and this step, there was some algebraic simplification. I think, let me think here. I think there may be an algebra error here. Let's see, when I multiply everything through by SC, I get S squared LC, and I get SCR in the numerator. And then when I divide by LC, I think I need an R over L in the numerator multiplying this S. So please, I've already uploaded these slides, so please on the upload, if you would, go and correct that, because this does need this R over L. I have two versions of this lecture. I have a new version of slides in which that's correct. This is an older version of slides that I'm using because it contains a few more things, and I guess I never caught this error last year when I used this version. So please make that correction on the PowerPoint slides if you download PowerPoint slides. All right, so this is sort of illustrative of, what the context that you might find this in. You have some circuit that consists of a network of passive elements. You've got an input applied to, so this is like a two-terminal pair circuit. You've got an input applied to a couple of the terminals, and then you take an output across a couple of different terminals. All right, so let me just do an example of a slightly more complicated circuit. So this is taken from your textbook. So this one is a little bit more complicated. We have, this would represent our network that you saw in the previous slide. So this is our network. And once again, notice inside the network that we're finding the transfer function for, there are no sources. So that's absolutely essential. Also, when we work with transfer functions, you notice this voltage is at the moment not specified. So because the voltage is not specified, we're just going to transform that to Vg of S, and we're not going to deal with the source at this time. Also, when finding a transfer function, you have to assume that all of your initial conditions on the inductors and capacitors are zero. That is because, once again, we're finding a transfer function that is independent of external sources. So by definition, we've got to have a situation where this has been drained of any energy. Otherwise, when we do the Laplace transform into the Laplace domain, we would introduce sources here because of the initial conditions, and we couldn't find a transfer function. So always when finding a transfer function, initial values are zero. So the first thing we need to do before we can find a transfer function is we have to transform this entire circuit into the Laplace domain. And so we've got a capacitor and an inductor. The capacitor value will go to 1 over SC. The inductor value will go to SL. And so that's going to be shown on the next slide. So here is finding the inductive impedance, SL. That shows up right here. The capacitive impedance, 1 over SC. That shows up right here. Now, there are a number of ways at this point to find the output voltage in terms of the input voltage. One thing you could do is you could find an equivalent impedance for everything. Basically take the series combination of these two, put that in parallel with this impedance, and then do a voltage divider. So that would be one way. In this particular problem, it turns out that it would be just as easy to define this node and have a node here and place your reference here. Now then, this node voltage is V0, this node voltage is VG, and so you can write a single equation, a node voltage equation that's going to put your, at this node, that's going to put your output voltage in terms of your input voltage really easily. So that's shown on the next slide. So here's the node voltage equation for that circuit. Let me go back. Let's step you through this. If I can work my, okay. So if this is V0 at this node, I would have V0 minus VG over 1000. And then I would have V0 over 250 plus 0.05 S. And then I would have plus V0 over 10 to the 6th S. So those would be the terms in my node voltage equation. Those are shown here. So as you can see here, you just move this term over to the right hand side. You flip sides, rearrange some things so that you get V out in terms of VG. So that would just be finding a common factor and doing some inversion and some algebraic simplification to get from here to here. All right, once you're here, you're pretty much done. You divide both sides by VG, and that allows you to obtain your transfer function. And so notice it has 1 0 at minus 5,000, and it has 2 poles, and we'll determine the poles on the next slide. But I want to look at the circuit once more. Notice that in this circuit we have 2 energy storage elements, the inductor and the capacitor, which by nature is going to make this a second order circuit. So if we were writing a differential equation for this circuit, we'd get a second order differential equation. Since we're solving in the Laplace domain, we're going to get a polynomial in S that's second order. So here's that transfer function. If you find the roots of the denominator, you get the following 2 roots, minus 3,000 minus j 4,000 and minus 3,000 plus j 4,000. And then the numerator, 0 in the numerator, looks like minus 5,000. Given that our denominator is a polynomial, a quadratic, it's going to factor into complex conjugate pairs. We know that basically this transfer function, if it were transformed back to the time domain, would yield a damped oscillator. So this is analogous to an RLC circuit that would have both oscillation and damping. So you can tell what that would look like now. Is that the actual output? No. What that represents is the natural response of the system. So notice, independent of any sources, we can look at the denominator and determine that this system is going to have a natural response that's going to look like an e to the minus alpha t cosine of omega t plus v. Or if you complete the square and do the inverse transform that way, it'll be e to the minus alpha t times some cosine omega t, and then another constant e to the minus alpha t times sine omega t. So once again, you can know the functional form in the time domain that is due to the passive network. So that would be like a natural response. It's built in because that's the way the circuit's constructed. Okay, here's another example that I would recommend that you look at working, because this is similar to the one we just did. It's not terribly complicated to do, and I want you to start thinking in terms of poles and zeros and of sort of what kind of response you would get out of a circuit like this due to the transfer function. Now notice this one has a current, and this one, the transfer function is voltage over current. So remember I told you that sometimes you do see this because your transfer function theoretically doesn't have to be unitless. I don't love that. Typically people do, unless you get into like bridge parameters in electronics, typically you do try to find output voltage over input voltage. At least we will in this class. But for practice, to find a transfer function, I think it's fine. All right, so once we have a transfer function, what do we do with it? Well, remember that the transfer function is output over input. So we could just work with that equation and discover that if you know your input, you can find your output by multiplying by the transfer function, the input and the transfer function. So as an example, if we consider our RC circuit with taking the output across the resistor, this was our transfer function. And so now let's say to that transfer, that in that transfer function, we input a pulse. So here's one, and here's one. So this is just a 1 second pulse with a magnitude of 1. And as we discovered, we can write that as the difference of two step functions. So we're going to take this input and put it into the circuit, and we want to know the output. So the first thing we have to do is we have to transform everything to the Laplace domain. So in the Laplace domain, the transform of u of t is 1 over s. The transform of u of t minus 1 is e to the minus s over s. So when we take that input and we multiply it by the transfer function, we get the following function. So basically what that does is that allows you a way to use this sort of odd, this input that in circuits 1 you would have had to have modeled this as putting a source here, turning it on by closing a switch and then opening a switch. In the Laplace domain, we're just going to input a square pulse. You'll get the same result. If you take the inverse transform of this, you'll notice that you'll get one term that looks like e to the minus 1 over RCT, and you'll get another term that looks like a time-shifted e to the minus 1 over RCT. So I'll leave you to take the inverse transform of this to look at what that solution looks like. So I'm going to stop this particular video here, because the next thing I want to talk about is that the other thing we do commonly is we use transfer functions to analyze filters, and we'll use them to analyze filters, both simple passive circuit filters as well as more complicated higher order filters that are active circuits. So I'll stop the video here on this introduction of transfer functions before we move to another topic.